Alright, so here today we have a right triangle with side lengths 1 and I, which means according to the Pythagorean theorem, A equals 1, B equals I, A squared plus B squared equals C squared, which means 1 squared plus I squared equals C squared. I squared is by definition minus 1. So we have 1 squared is 1, minus 1 equals C squared. 0 equals C squared. C equals 0. So we have a right triangle. Right triangles obey Pythagoras' theorem. A is 1, B is I is the square root of -1. If you square, you get -1. 1 squared is 1. 1 plus -1 equals 0. How is this possible? It's not possible. It's kind of a mathematical joke. Obviously, it's a joke because there's a difference between something that's algebraically true and something that's geometrically true. So this is an algebraic relation, a squared plus b squared equals c squared, and these values for a, b, and c make this algebraically true. It's also the case that this is a geometric relation when you apply it to a physical object, which in this case is a right triangle. So a right triangle is a physical object where the sides here denoted by A and B are lengths. So that's a real dimension, and the hypotenuse also has a length. So it can't be possible for sides to have lengths and the hypotenuse to have 0 length geometrically. It's physically impossible, yet it's algebraically possible. So this means that typically the Pythagorean theorem is limited to positive real numbers. Positive real numbers, real as opposed to complex numbers, and positive because you can again plug in negative values for one of these side lengths and algebraically it'll come out, the relation still holds, but in real life you don't really have a negative length. Lengths are positive physical quantities. Doesn't really make sense. So geometrically the Pythagorean theorem is limited to positive real numbers. But what's interesting is that even though this is not a real geometric physical relation for an actual right triangle, we can actually expand the Pythagorean theorem to include more than the real numbers, to the complex plane actually. And the way that we can do that, is by defining what it means to square something. So let's say z is a complex number and we want to square it. We'll define that to mean the modulus squared, which is equal to the complex number times its complex conjugate. And what the complex conjugate is everywhere in the number z, you see an I, you replace it with minus I. So if we take the original complex number, multiply by its complex conjugate, that's equal to the length, the norm, modulus squared, which is absolute value squared. And that's what we'll define as squaring a number, instead of what we just did before. So if this is the case, then we have a squared plus b squared equals c squared. A is 1. B is I. And we don't know what C is yet. It's not 0. Remember, it's a real physical length. Cannot be 0. It's geometrically impossible. The complex conjugate of 1 is 1 because there's no complex part to it. It's a real number. So this becomes 1 times 1 equals 1. Let's see, for mod I squared, we get it's equal to I times minus I. I times I is minus 1 times minus 1 equals 1. So then let's plug these in. We have 1 plus 1 equals c squared. This is obviously equal to 2 equals c squared. And c is clearly equal to root 2. Which makes physical sense. If this were if this weren't in the complex plane, if this triangle were not in the complex plane, the length of this is still 1, which is, if this were 1 and this were 1, this would equal root 2 physically, not in the complex plane in R2, and we would get the actual length of the hypotenuse to be root 2. So if we define squaring like this, it allows us to expand the Pythagorean theorem to include complex numbers, which is not super useful like in everyday life because lengths of things in the real world are not complex. They're always real valued numbers. But this is just an interesting mathematical joke and then way to solve the joke. I just thought it was interesting. But yeah, thank you for watching.